Okay, good afternoon, everybody. A couple of announcements as we begin. Your first homework assignment is due on Friday, and as a reminder, that should be uploaded as a black and white PDF to Blackboard. The assignment will vanish right at 12 o'clock, so your option to upload it after 12 o'clock will be lost. So please don't wait until the last moment there. And after you submit, make sure that it actually went through. And there's a confirmation dialog when you submit an assignment on Blackboard. I don't accept late assignments unless you have an official university excused absence. So please take care about that. Also, on Friday, we're going to have our first quiz of the semester. Now, ordinarily, I don't announce quizzes, but I thought since we're still just getting into the swing of things, I'd give you a little heads up for this one. So we'll have a brief quiz that'll probably take no more than 10 minutes at the beginning of class on Friday. The next homework assignment related to cash flow diagrams, compounding, and some other topics will be due a week from today. And you can find that assignment, I'm sorry, not a week from today, a week from Friday. So I've added that assignment now. If you've already finished homework 1, you can get an early start on number 2. But so you've got 9 days for that next assignment. The topic for today, economic equivalence, comes from section 7 in chapter 1 in your textbook. And so remember that it's a really good habit to review the textbook's point of view after class. After we've had this lecture, we worked an example, you've had a brief overview of the topic from me, it's good to hear it from someone else because that's going to help with retention and make sure that the concepts sink in the way that they should. So before we get into economic equivalence, are there any questions related to the announcements? Okay. A couple of key terms that we've touched on already before, but let's make sure that it's all at the forefront of our mind. Oftentimes we're going to be doing calculations that have to do with projects that last more than a single year. Remember that money in the future isn't as valuable as money now because of inflation. Prices are always going up in the future, and so if it costs you more to buy things in the future, then that same dollar that you're spending now won't buy as much in the future. So you want to be repaid with more money in the future than you spend now to make up for that difference. And so the amount or the value of money in our current terms is referred to as either a present value or present worth. Sometimes if we're applying it to an entire sequence of amounts, we can call it a net present value. That net present value means when you've moved all the money from the future to the present. Essentially the same thing with the discounted cash flow. If you have a diagram or a sketch that's showing lots of different amounts throughout time, once you've moved it all to time 0 and found the equivalent amount, that's a discounted cash flow. So it means money in today's terms. A single amount some year in the future is a future worth or a future value. And I said year just now, but remember that a period can be any duration of time. It could be that we're compounding periods every month. It could be every quarter, every year. And so at some point in the future, an amount would have an FV or an FW. And that's when we compound amounts into the future. We're calculating the future amounts. When we have a positive inflation rate, then those amounts will be greater than the amounts were at the present. An annual worth, sometimes also called an annual uniform series, is a recurring amount that's the same amount every year. And so we did some sketches in class on Friday, and an A sequence is when every arrow is the same length. An A sequence doesn't start at the present though, it starts in year 1. So it'd be the same amount repeating however number of periods. It can be 2 periods, it could be 10, it could be any number. But the key thing here is that they're equal amounts and they're applied at the end of the period. So that's why we don't see a uniform series starting at time 0. The uniform series starts at 1 on the diagram because it's at the end of the first year that the transaction occurs. Economic equivalence is the topic for today, and it's having to do with the time value of money and interest rates. And you can think of economic equivalence as being, if you want to have the ability to purchase the same amount in the future. It's not the same number of dollars, but economic equivalence means that however many dollars or euro or whatever the currency is, the amount of money you have now and the amount of money you have in the future may be different numbers of dollars, but their purchasing power is the same if they're economically equivalent. So it has to do with what are you doing with the money in the future. Can you do the same things in the future that you can do now? If so, then you've got economic equivalence. And the way that you ensure economic equivalence is to use the interest rate and the number of periods to find out how much some present amount would be in the future if you're compounding it over time. We'll do some of those calculations today as an illustration of what these definitions mean. Okay, now here's just the same information but defined in terms of the variables we'll see in a lot of the problems this semester. T would be the amount of time or the number of periods. Sometimes T and N are used interchangeably because they're both referring to the passage of time. P is the present value, meaning at time 0 of the present. F, future value. A uniform annual series. I is the interest rate. So it's expressed as a percentage. It's not the interest amount. Capital I is the variable that we assign for interest amount. Little I, lowercase I, is the interest rate. So it's the interest amount expressed as a percentage of the original amount that was borrowed or loaned. Okay, so economic equivalence. Let's say that you make a deposit now of $100 and the interest rate is 10% per year. Now this rate that we're talking about, it could be the interest rate that's being paid on an account, or we could be talking about the inflation rate. And so maybe if we're focusing our attention on what prices are going to be in the future, we can also express those changes as a percentage. So the point is, though, it's just the amount of money is changing 10% per year. So economic equivalence would say that if you deposit 100 now, you should be able to withdraw 110 in the future for there to be economic equivalence, because prices are going up at 10% per year to buy the same amount of stuff after 1 year as you could buy now at the present. You'll need more dollars. So that's an illustration of economic equivalence. Now in this illustration, we're saying that $100 now is economically equivalent to 110 withdrawn in 1 year if the 100 was invested at 10% per year. The direction of the arrow, down means money out from you, so that's a deposit. Up means money coming in to you. So you're receiving money in year 1, you deposited money at time 0. We're not saying that a deposit and a withdrawal is the same thing. What we're looking at in this illustration is just the magnitudes. Of course, giving money and receiving money is not the same thing, but what we're saying is that 100 at time 0 is the same as 110 after 1 year if you've received 10% interest. Any questions so far about economic equivalence? Yes?
So when you were making like a cash flow diagram for something, where you're given essentially the equivalent amounts given inflation.
Yep.
Would you make those two arrows the same size, or would they be different sizes?
Good question.
Like the quantity or the value?
Yeah, you're remembering that what we like to do is try and make the size of the arrow an indication of, relatively speaking, the amounts. And so, depending on how good we are at sketching, we'd want to make this arrow at time 1 a little bit longer than the arrow at time 0. So if this was an inch, then that would be 1.1 inches in our scale drawing.
So it's more directly about amount
Yeah.
rather than relative value then.
That's right.
Okay.
Yep. Okay. So we just did this. Now this is a different example. You can receive $100 in year 1 or a certain amount today. So I'm giving you the choice. You can take $100 after 1 year or a certain amount today. If the interest rate is 10%, how much should you receive today? Okay, so let's first of all break this problem down into the labels. The applicable labels here are N, I, F, and P. Okay, so what is I in this example? 10%, or if we're putting it into one of the equations, we would write it as 0.10. All right? What are our periods? What's the unit of time for our periods? Okay, years. All right, so how many years have we got? 1 year. Good. Now, what about P versus F? Which is given and which is the unknown? Okay, so P is a question mark, F is 100. The formula I've shown you in class before is F equals P times 1 plus I to the N. Now the reason why I write that formula on the board is you might be mentally tempted to go after a shortcut here. I think if I let you, some of you would say that it's $90 today because 10% of 100 is $10, so maybe it should be $90 today. But that wouldn't be the right answer, because if you put in 90 today, okay, the interest amount would be 9 after a year, and so then the total would be 99. 90 plus 9, so it wouldn't quite yet be 100. So in this illustration, what we can do is we can say, on a graphical basis, P is the unknown, our interest rate is 10%. You can either get 100 now or some unknown, 100 after a year. So F, I should even change that with a label. That would be a better illustration if I said F equals 100. All right. So here's the formula, and we do the substitutions, then we can calculate. We need to make it 90.91 so that after the 10% interest is added on, it will be 100. So 90.91 times 1.1 will be $100. So if I only offered you $90, then you'd say, no, I'll wait the year and take 100 because that's the better deal. Okay. But if someone's willing to pay you $95 now or 100 in the future, what you could do is you could just take the $95, put it in your own bank account that's earning 10%, and then after a year you'd have more than they were going to offer you. So you'd be better off taking the money now than waiting for some time in the future. Okay, any questions so far about economic equivalence? So think about the practical application of this. It has a lot to do with sometimes if you've gotten a bid from a contractor on a job, you're getting your driveway refinished, or if you're getting plumbing done in your house. Sometimes bids will only be valid for a certain period of time because they can't lock in the price of materials or know exactly how much things are going to cost an indefinite amount of time in the future. So maybe a bid's only good for 90 days. And then you have to get the job quoted again because the time value of money, especially when prices are fluctuating a lot, as they do in a lot of engineering adjacent fields, you have to pay attention to economic factors like this. Okay. On Friday, I introduced the idea that graphs are an easier way to summarize a problem than sometimes the English language. You can just look at the cash flow diagram really quickly and understand what is given and what is unknown. So as an illustration here, this kind of problem, present is given, the future amount is unknown. So we would summarize this as find f given p. It's really important that this order is what comes into your mind, because there's a series of equations and formulas that you'll have in the book and on exams where you're calculating the ratio of f to p. And so you always put the unknown in the numerator and the known in the denominator. So here we know the present value, so this is an f/p problem. That's kind of how I'm going to say it is, let's do the f/p operation. And what that may mean is you look up a factor in the back of the book, or you calculate the factor with an equation, and then you multiply p by that factor to find f. Okay, so this is just an illustration of p/f. Okay, now what kind of problem is this?
Find p given f.
Find p given f. Right. So it's a p/f because p is the unknown, f is the known. Okay? Here is find a given p. So this would be a/p. Remember that a, the unknown, is in the numerator, p is in the denominator, and the reason why is that you'll have like a/p is some number, 3.4872. You'll look up some factor, and then you'll multiply the p, and then that is how you will calculate the unknown a. So it's a ratio is what it is. And you want to have the unknown in the numerator so that you can move the known over and multiply it by this ratio that you calculate. So that's why we're taking the time to formalize a consistent language for how we break these problems down. Okay, now what about this one? What kind of problem is this? Remember, the unknown is first, so find p given a. So this is a p/a type problem. All right, now notice with an annual series, that dashed line doesn't start at time 0. That's the general form of an annual series, is that the annual series starts at 1, and then it continues from there. So if you did have a problem that also had an arrow at 0, then that arrow that's at time 0 isn't part of the annual series. It's just some single amount that's already at the present. So the annual series only includes the amounts that are in the future. So sometimes there will be combinations of different problems together. On the same cash flow diagram, you might have both an annual series, an amount at the present, and some amount in the future. There can be any number of combinations of these variables all on the same cash flow diagram. Are there questions so far? Okay, let me show you the in-class exercise that we have for today as I hand it out. We've got 3 questions on the front side of the paper, and then 1 2-part question on the back. So I'd like you to start with the first 3 questions on the front of the paper. I'll be circulating around with the answer to see how it's going as you're doing the calculations, and then we'll stop and have a discussion about it before then you move on to the back side of the paper. If you do work ahead, though, if you get to the front side of the paper really quickly, you can move on, but we're going to do this one in 2 parts, just in terms of what I show you on the screen. I hope you've got a 3-ring binder, because it's going to be increasingly difficult to keep track of all these papers if you don't have someplace good to put them all. We've got, I think, this semester 42 classes, 2 exams, so you're going to have like 41 papers. So getting a 3-ring binder is going to be a good investment. Okay, on the first problem, there are a couple of ways that you can correctly express what it's saying in the problem statement. So you would have to pay $550 now, so the arrow is down, meaning it's an outflow, and then you get an extra $85,000 a year for each of 6 years. And so 1, 2, 3, 4, 5, 6 times that you're getting this $85,000, so it's a uniform annual series. And then there's a single amount of $50,000 that you're getting for scrapping the equipment. That's a revenue to you because it's like the equipment you originally paid for, you're just getting rid of it, and it's kind of like a salvage value. Now, I wrote on the whiteboard that what you could also do is you could say this is a 5-year annual series and then combine the single amount at year 6. And so it would be F equals 135, and then it's only a 5-year annual series. As I've sketched it out here, it's the original 6-year annual series that it was said in the problem statement, and then that single future value is on top of the annual series. Between the two options, both are technically right. I'll probably more often go with this approach because it may be that you get some updated information on how much the salvage value actually is. So my impression is it's better to keep the parts separate in case some of the given information is revised. Any questions on the first one? It's a little tricky when it says at the end of the 6th year. So here is the first year. From 0 to 1 is the first year. From 1 to 2 is the second year. 2 to 3 is the third, fourth, fifth, 6th year. So the 6th year goes from 5 until 6, and the end of the 6th year is at the mark for 6. And by the way, on a problem like this, you should not only put the labels like A, F, and P, but you should also put the numbers to indicate how many arrows there are, so that you or whoever's looking at your problem doesn't have to count and try and remember how many years there are. So be sure and put the numbers as well. Okay, the second problem was saying if you want to receive $95,000 next year on an account that pays 9% interest, draw a cash flow diagram, and how much should you deposit today? So here's the cash flow diagram. We don't know how much to put in now, so it's down arrow means we're going to deposit. After 1 year, we want to withdraw a known amount of $95,000. So the unknown here is P. So find P given F is this kind of a problem. And with the formula, we can put in the known, divide by 1.09 to the n. N is 1, so it should be 87,155.96. Now remember what I said on Friday about rounding off. If you round off, then you're not going to get an accurate number to the penny. So in more complex calculations where you're doing like n to the 2 power or to the 3 power, this factor in the denominator may get more complex than 1.09. You're going to have to preserve all the digits to get an accurate to the penny calculation. So let's look at this third question now. The third question is asking what's better, option A or option B? And option A is buy the fuel now and store it because it's a cheaper price. And I kind of feel like I'd like to do that right now. Gas prices, I've seen some stations that are charging $2.30. I mean, historically, that's not so bad. I remember when gas prices were over $4 a gallon. And I went to Washington, D.C. a couple of years ago, back when gas prices were high, and I paid almost $5 a gallon then. So I'd like to store fuel if I could. It's just not feasible. But let's say, for instance, what if you could store the fuel for a fee? So that's option A, is buy it at the low price. Option B is take the same amount of money as you would have spent, put it into an account, and then see how much money you have. And is it going to be enough to buy the fuel at the higher price? That's the question. So which is better? So if you buy it now, it's going to be essentially $260,000, 1 penny short of that. The buy later option is saying it's going to be more expensive fuel. The fuel cost will be $265,000, but what if you took this $260,000, put it into the account, how many dollars will you have? So it turns out you'll have more than enough to buy the fuel. You'll have $318,000 in that account, but you only need $265,000, so you're going to have more than $50,000 left over. So that's a proof that option B is better, because you'll have the fuel you need, and you'll also have some additional cash left over. Now here's what I mean about rounding off. So if you just rounded this off, this factor, to 1.22, then you're not going to have your answer be accurate to the penny. It would only be accurate to $318,000 if you'd rounded this to 3 digits. So the key practice you need to remember is in your calculator, keep all of that precision. Don't round off to the very end when you round it to the nearest penny. Okay, so option B is better. Everybody get that same thing, option B? Yes? All right, so now the time is yours to work on this problem on the back here. This is kind of a thought problem here. See if you can extend what we've done so far. So in the first part, I'm asking you to apply the equation separate times the equation F equals P 1 plus I to the n power. Okay, so what we're saying is this amount that's here at year 1, I labeled that, like, I called that A, amount A. And then the amount in year 2, I call that amount B. And the amount in year 3, I call that amount C. And then this arrow at year 4 is D. So how many years does amount A have to go to get from year 1 over to year 4? Like, what's the N? So N is 1, 2, 3. So the way we would apply this formula is we're saying the P is 12,500. What we're trying to find is F. So find F with the given P of 12,500, where it's N equals 3 years and the I interest rate that's mentioned in the problem statement is 5% interest. So you're essentially moving the arrow, that's called compounding, into the future. 12,500 that is in year 1 is worth how much if you move it to year 4? So to get it from year 1 into year 4, you're compounding it 3 years to the future. So you've moved that arrow A over to year 4, and then arrow B, which is 12,500 in year 2. The N for that isn't going to be the same as the previous N was. The N for this is just going to be 1, 2. So you end up combining all of the amounts, moving them to year 4. The other approach, though, this is saying the ratio of F to A is 1 plus I to the n power minus 1 divided by I. So if you know I and you know n and A, you can solve for F algebraically. All right, I don't want to say any more than that because I want to leave a little bit of mystery for you to finish the calculation. So I'm going to pause the recording and give you some additional time to work on this one. Okay, I'm putting the solution up on the screen for you to take a look at. We've only got a couple minutes left. So I labeled the arrows just to make it clear, like which arrow is moving where and how many years. So you see the amount in year 1, to get it over to year 4, it has to compound 3 years. Then arrow B only compounds 2 years. Arrow C compounds for 1 year. And then arrow D is already at time 4. And so I don't have to do any calculations to change the amount of arrow D. It's already 12,500 at year 4. So then adding them all together, this is the amount from year 1, year 2, year 3, and year 4. The combined amount is 53,876. And then the other way of doing it, instead of like moving each year individually, which is a little time-consuming, kind of tedious, to do each one of these like an individual F. That's what we did in this first approach, is we treat each arrow as though it's a single future isolated amount. But we can, instead of that, we can say, well, that's an annual series where each one of those is an A, 12,500, and so we get the same 53,876 by using the formula to solve for F given A. And so N is 4, I is 0.05, and we can get the same amount either way. All right, I'm going to leave that on screen for a minute in case you need to copy anything. And of course, as a reminder, the calculations will appear in the YouTube video that's posted, so you can always get it there as well. It's 12:50. We're out of time. Remember, the homework is due on Friday, and we're also going to have a quiz at the beginning of class. So feel free to stop by if you have any questions. I'd be glad to help you out. I will see you on Friday.